better. All right, so we're on 1B.8, understanding rate of change. Okay, so for understanding rate of change, we're just building on knowledge that you already have about finding the rate of change, right? The main thing here is that we are learning to use it in situational, real world situations. Sorry. Yes. Okay. We're on part one. It's 3-part notes. What says it? All right. So we're gonna dive in. So there's 3 parts. We're gonna start part one. Part one is gonna go on page 21 of your handy dandy notebook when we're done and set, all done and set. So with part one, we're talking about rate of change from linear to nonlinear functions. We've talked a lot about rate of change with linear functions. And in general, what does rate of change mean? Well, rate of change measures how one quantity changes in relation to another quantity. So when we talk about rate of change, you'll see me write ROC a lot, rate of change. If you continue into AP Physics and not physics, pre-cal, or calculus, you'll also continue to see ROC. But rate of change essentially is just asking what is our change in our Y over our change in our X, okay? In math and in physics, especially, we use the triangle, which we call delta. So you may hear your physics teacher say delta Y over delta X or delta V over delta T. It just means change in Y. The delta, think of it, it's the Greek delta. It's a Greek letter. It's not a triangle. It is a delta, and it means difference. Okay. So if I'm finding the difference, that means I'm doing what operation? There we go. I knew you knew it. See? That says difference. We're going to roll with it. Okay. All right. So that's what we're diving into. So before we get started, let's just talk about linear functions from when you were in Algebra 1. So in Algebra 1, you learned that a linear function has a constant rate of change called the slope. That's our magic word for the book. We all agree? Okay. AKA the M. All right. That's your y2 minus your y1 over x2 minus x1. And what were you doing right there? Subtracting, right? You were finding the difference, that delta. All right, next. So if I gave you this simple example from pre-algebra or algebra, example, distance traveled at a constant speed. Distance traveled at a constant speed, the key word that lets me know that this is linear is that it is a constant. And speed is a rate that you're moving, right? So we know that this is a constant rate taking place. Because there's a constant rate, if I know what that constant rate is, I can make predictions about what's going to take place, correct? So for example, if I told you that I am moving in a car and it's traveling at 60 miles every hour, right? If you know that it's traveling 60 miles every hour, I would ask you, first hour, how far have I gone? 60 miles. Second hour, how far have I gone? 120 miles. Third hour, how many miles have I gone? 180 miles. I can make these estimations because I have a constant rate that is taking place, right? A constant rate means that I'm continuously adding or subtracting the same amount over a period of equal time, right? So in the conclusion here, we would say that the rate of change is constant at 60 miles per hour, correct? That is what it is. So my constant speed relates to my rate of change. All right. How many of you ever thought of the fact that when you're in a car that is linear speed in motion? Anyone ever thought about that? I do that when I'm stuck in traffic. I start trying to guesstimate how far I'm going to have gone if I'm driving at 15 miles per hour or 15 miles per minute. 15 minutes, how far am I going to go? Why? Because I have nothing else to do stuck in traffic. So I turn things into math problems. It's a unique feature of me. So I know. One day you can be there too. I did have a student. She sent me a text when she was in college. She's like, I cannot stand you. Because she went to SFA and she had like a long drive from Waco to SFA. And she says, I really don't like you because on this drive, why the heck was I trying to predict my distance using my miles per hour? I was like, you're welcome. I do what I can, changing the world. All right, identifying rates of change. So when we're talking about identifying rates of change, there are 3 types of rates of change that we reviewed in our discovery lesson, correct? And our 3 types are positive, negative, and constant. When you have a positive rate of change, you are your y values increase as your x increases. So when I'm looking at a graph, reading a graph from left to right, that means as my x's are going up, my y's are going up, correct? That is going to be my positive rate of change. Next, you have a negative rate of change. Your negative rate of change is your y values are decrease as your x values are increasing. So when I look at that graphically, my y values started high, but then lo and behold, they are going down, right? That is going to be my negative rate of change. Then I have a constant rate of change. For my constant rate of change, nonlinear, I didn't put constant. Constant is horizontal. I don't know how I forgot constant on everybody's, because if it's not on mine, it is not on yours, right? That means your y values stay the same. I'm just going to draw an arrow up to as x increases because I don't have enough room. So as your x's increases, your y values are staying the same. So when we are looking at a constant rate of change, that means we have a flat line. We have a 0 taking place. I'm sorry that I forgot that in your notes. All right, nonlinear. So when we're looking at nonlinear rate of change, the rate of changes at different intervals. Okay, an example of this would be when you had your waves. Remember, your waves were different, correct? And when we were looking at Karen's marathon, right? Karen was running, and you can see when Karen stopped running, she's like, "Oh, I'm tired." And she's like, "Oh, I got to catch up." And then, "Oh, I got tired," right? You could clearly see the change in her speed over that time, right? We just discussed that speed is an example of a constant rate of change, right? So an example of a nonlinear rate of change. We're going to come back to this example again in part 3, but I just want to bring it up now, just to kind of get us talking about it. So thinking about temperature throughout the day, right? When you wake up in the morning, I wake up to an Alexa who tells me what time it is, and she tells me the temperature and what the temperature is going to become. Why? Because I want to be a wizard, and this is the closest thing to being a wizard I'm ever going to get is having Alexa. So Alexa wakes me up, and she tells me, "Oh, good morning. It's 6:30 a.m. The temperature outside is 67 degrees. By 1 p.m. today, the temperature will be..." No, mine tells me 5 things that are going on in the world and then plays music. That's a lot. So, no, not my Alexa. My Samsung Bixby tells me the 5 things that are going on in the world. Alexa starts playing music. I need it. My ADHD is like, "Get up. Hold on. We're up. We're up." So anyways, morning. So in my mind, you're like, dang, that's gonna go real quick, right? I went from 67 to 90, right? So oh my gosh. Like every generation has a number. So crazy. I don't understand. Morning. So it's going to be a rapid increase, right? Or fast increase. And what makes that fast increase? Science people. The sun. Yeah. Oh, my 5-year-old could have told you that because they're learning about weather and what causes our weather, you know. All right. In the afternoon, is there much change happening to take place? No. So it's like pretty limited change, right? So you can write limited, you can write steady, you can write it's pretty limited. It's slow, right? Okay. Well, it's limited. It's more of a constant situation, right? I didn't even say it. And then evening. So now the evening comes, it's now 5 o'clock, and slowly but surely, what ends up happening? The sun sets, right? The sun is setting, and therefore our temperature is slowly decreased, right? It's slowly decreased. All right. This is an example of a real world non-linear rate of change. Most rates of change that we are talking about in the real world are not going to be perfectly linear. Okay. There's going to be other factors that cause it to stop, go, speed up, backtrack. There's going to be reasons why it's not going to be. Okay. All right. what you're going to do at your table is I'm going to give you, let's say 90 seconds. You're going to look over examples 1 and examples 2 and decide as a table, do they represent linear models, why or why not? Okay. So looking at examples 1 and example 2, do they represent linear models, why or why not? Go. All right, here we go. Let's talk about it. All right. Group 1, what did you guys decide for example 1? Was it linear or not linear? And why is it not? It is. So what's happening here? It's quadratic. Okay. It could technically be, depending on how you looked at it. So if you did quadratic, that means that the second difference would be the same, right? So if you said quadratic, that means when I took the first distance, I have 4 minus 2 is 2, 8 minus 4 is 16 minus 8 is 8. Is my second difference the same? So it wouldn't be quadratic. What would it be? It would be exponential. Quadratic means I have a second difference. Okay. It would be a exponential. It's powers of 2. You have 2 to the 1, 2 squared, 2 to the 3, 2 to the 4, right? I am multiplying by 2 each time. But it is nonlinear, and that's because instead of having a common rate, I have a common ratio. Do y'all remember that for exponentials? So it's nonlinear. Specifically, we have a exponential. Okay. All right. Example 2, group 4. What y'all decide? We don't have a constant rate of change. Am I adding or subtracting the same each time? Yeah, you're draining your battery power, right? So at first hour, I have 20% of battery left. Remember, your teacher made a typo. She does not know why there's negatives on your thing. And you pretend that they're not there. Okay. First hour, and I just realized that I'm talking about draining of a battery. We lost what? 5%. Next hour, we lost 5%. If it bothers you thinking about it as a percentage, you can also think about it as a decimal. I was at 0.20, then I was at 0.15, then I was at 0.01, and therefore I'm losing 0.05 every single time, right? Over the rate of time. So I'm losing percent. So this was actually a linear, and it's because it has a constant rate of change. All right. So let's talk about things to remember from this. Remember that linear equals a constant rate of change throughout. So the entire, it's going to be the same value no matter where you're at, no matter what 2 points you choose, it's going to be the same value of change. Okay. Next, nonlinear equals rate varies at different intervals. So nonlinear, your rate is going to vary at different intervals. Okay. So think about Karen, right? Karen, her rate changed at different intervals depending on how much extra energy she had, right? All right. When you are looking at the interval, look at the x values. You're going to look at the x values for the interval. I think I got to write that grammatically correct. Look at x values for interval. Okay. So when you're given the interval, you're looking at the x value. Your x marks the spot. Okay. All right, this is going to come important when we move on to the next part of reading the intervals. Okay. All right, questions about part 1.